All right, hey there, Integrals 1, day number 4. Topic for today is integration by parts. I'm going to get into the how and the why here in just a moment, but let's just go back to kind of where we've come from. Let's talk about the different methods that we have in our toolbox. So we've got traditional, just your basic antiderivatives. We've got U sub. We've got change the variable. We've got integration by partial fraction. Okay, along with that is the rare but useful integration by completing the square and integration by long division. Okay, so in this lesson we're going to bring our seventh method, which is integration by parts. So let's go ahead and get started. Okay, so integration by parts comes directly from the product rule. In essence, we are undoing a portion of the product rule. So let's look at the product rule of two functions, u and v. Okay, so in the whole process here, we're going to be identifying functions u and v. So if I took the derivative of u times v, I get u dv, which would be u times the derivative of v, plus v times du. Right? That's our product rule. Now if I integrated both sides, individually, the integral of the left side, which is the integral of a derivative, would just be uv. The integral of the right side would be as it is. Split up, two separate integrals. Okay, now the way that we rearrange this, and it can be rearranged multiple ways, but the way that we like to rearrange it is that the integral of u dv is equal to uv minus the integral of v du. Okay, so what we want to do is we want to identify a couple of things. We want to identify function u and function v within the context of an integral problem. Okay, now it might not make sense yet. However, we'll look at an example and we'll determine what and how and when. So we use lipit to identify what u and dv are, right? So as I'm working here within the context of a problem, so this is what you'd be posed with. You'd be posed with the product of two functions, right? That integral. Okay, and of course at this point, the first 6 methods, nothing's going to work, so we got to go to integration by parts. And as you get more experience, you'll just recognize integration by parts relatively quickly. So what we do, let's take a look down at this example here, is, for example, let's look at x e to the x. Now you can't use u sub. There's no long division. There's no partial fractions. None of those methods will work. So what we want to do, again, I'll put the integral of u dv is equal to u times v minus the integral of v du. That was developed from the product rule. So how do we identify u and dv? Well, u is either going to be x or e to the x. So how do I know which one's which? I use this idea called lipit. L-I-P-E-T. And it gives us a way to identify which one is which. So u will always be up in this orientation, and dv will always be down. So L stands for logarithms, I stands for inverse trig, P stands for polynomials, E stands for exponentials, and T stands for trig. So where does x land? Well, x lands within the world here of polynomials, and e to the x lands within the exponential world. And I always tag on the dx to dv. Okay, so e to the x dx is dv, and x is u. Okay, so the integral of x e to the x dx will be equal to u times v. Okay, I'm taking this directly from up here. uv minus the integral of v du. So it takes some of the guesswork and the algebra out of it. I'm just identifying u and v, or u and dv, and I have to then find v and du. So if I know that u equals x, I'm going to need du. Du will equal dx. If I know that dv is e to the x dx, then the integral of e to the x, so dv gives me v if I integrate it, so I get e to the x. So I now have u, dv, du, and v, and I can construct the rest of this integral. So what would u times v equal? Well, that would be x times e to the x minus the integral of v du. Well, that would be the integral of v, which is e to the x, times du, which is dx. So I have nothing to do here for uv, but I have to integrate e to the x dx, which is e to the x. And since this is a indefinite integral, I just leave my answer right like that. So x e to the x minus e to the x plus c is our answer. Okay, let's look at another example on the next page. Okay, so let's look at these two examples, one being x ln of x and the other being just ln of x. So let's look at the first example, number 2. U, which is up, lip it, dv, which is down. So it looks like I've got x and I've got ln of x, and then after I identify which one's which, I tag dv with dx. So dv will be x dx, and u will be ln of x. So u equals ln of x, and dv equals x dx. Therefore, du is 1 over x dx, just the derivative of u, and v will equal x squared over 2. Okay, so I know that the integral of x ln of x dx will be equal to uv, which is x squared ln of x over 2, minus the integral of v du. Okay, so v times du is x squared over 2 times 1 over x. The x is reduced, giving me x over 2 dx. So my answer comes out to be, looks like x squared over 4 for that particular antiderivative. And there you have the integral of x ln of x dx. Awesome. Let's look at number 3. Okay, this is an interesting problem. We're going to identify u and dv, again, using the same method. Okay, some can be fooled the initial time or the first time you see something like this, but really what I have here is, I don't have two functions, at least from what it looks like, but I do. I have 1 and I have ln of x dx. So 1 is a function and it's a polynomial. Okay, ln of x also a function, and it is a logarithm. Therefore, u is ln of x, and dv is dx. Okay, so let's identify du. If u is ln of x, then du is equal to 1 over x dx. If dv is dx, then v is x. Okay, so let's continue our work here. The integral of ln of x dx is uv, which will be x ln of x, minus the integral of v du. Well, x times 1 over x is 1, so I get 1 dx. So the integral of ln of x with respect to x is x ln of x minus x plus c. There you have it. Okay, you should be at this point starting to get used to this process using lipit and doing some derivatives and antiderivatives in the process. Let's look at the next slide. All right, number 4, very similar to number 3 in that we can rewrite this function as 1 times arctan x. So if you just see one function, you assume the other function in the process of finding u and v is the function 1. So using lipit, I've got, looks like an inverse trig function. So that's I, which will be arctan x, and a polynomial, which is 1. So I'm going to tag dx there. So dv is dx, and u is arctan x. Okay, so if I work with u and dv, as usual, u is arctan x, so du is 1 over 1 plus x squared dx. Okay, we got to know our basic derivative, so make sure you're on board with that. If dv is dx, then v is x. Okay, so as I look at the integral of arctan of x dx, I get uv, which is x arctan x, minus the integral of v du, which will be x over 1 plus x squared dx. Okay, now the method of integration by parts may require you at some point to use another method within it. So I am going to, in order to integrate this function here, I'm going to use a u sub, and I'm going to say u equals 1 plus x squared. Therefore, du is 2x dx. Therefore, 1/2 du is equal to x dx. All right, so what we're going to see here then, again, I've got x arctan x hanging out minus the integral, and I'm going to pull that 1/2, this 1/2, out in front. This will be du, and I'll have x dx replaced with du with the 1/2. That'll be 1 over u. Therefore, the antiderivative, or the integral of arctangent of x, is x arctan x minus 1/2 ln of u, and u was in our u substitution 1 plus x squared. Okay, now technically I probably should have used a different variable instead of a u sub. Okay, maybe I use a w sub, so dw, dw, all that good stuff. So this would be w dw, and the reason why is because I've got a u being represented within the integration by parts substitution. Okay, let's look at number 5, very unique example. And we are going to use integration by parts. So let's first identify u and dv. So Lipit. Okay, so it looks like I've got an exponential function, which is e to the x, and a trig function, which is sine x. So I'm going to tag sine x with dx, and u will be e to the x. Now, in the case of the exponential and trig, these are actually interchangeable, and it doesn't matter. Okay, one as opposed to the other, doesn't matter which one's which. I'm going to use e to the x as u. So if u equals e to the x, then du equals e to the x dx. Pretty simple. dv sine x dx, therefore v would equal negative cosine of x. All right, so let's construct this. The integral of e to the x sine x dx is equal to negative e to the x cosine x minus the integral of negative e to the x cosine x dx. Now that negative is going to come out and make that positive. Okay, so now what? It looks like, to me at least, I'm going to have to use integration by parts again. Okay, so I'm going to set u equal to, in this case, e to the x, and dv equal to cosine of x dx. So du, again, e to the x dx, and v sine of x. So let's reconstruct this. You might already see the issue that we're going to run into, which is that this will never stop. But it will. We have a tricky way of doing this. Okay, plus. Now this integral is going to be uv. And again, I've used u and v multiple times. You should be careful with that. I'm not necessarily modeling the correct way. I should probably be doing w and dq. I don't know. I'm not getting there because at this point I want to try to keep it simple. Okay, so that's uv minus the integral of v du. So that would be e to the x sine x dx. Okay, so now what the heck, right? There's a whole lot of stuff going on here. I'm going to just clean this up, put everything in one form. Okay, so I get, let's see here. This is, let me rearrange. I'm going to put e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. Now, could I do this all day? Absolutely. Absolutely. But let me take you back to the old algebra days. What would happen if you had x equals y minus 5 minus x? What would you do to solve for x? Well, yeah, you just add x to both sides. So you get 2x is equal to y minus 5, and then that would mean x equals 1/2 of y minus 5. That is no different than the situation I have right here. Okay, so you may or may not see what I'm talking about yet, but consider this like x, and consider this like y, and consider this like 5. All right, I can do some manipulation algebraically to isolate what I'm looking for, which is the integral of e to the x sine x. So I'm going to add e to the x, integral of e to the x sine x to the left. So that would give me 2 e to the x sine x's. 2 of those integrals is equal to e to the x sine x minus e to the x cosine x. And I'm going to tag plus c on there since this is an indefinite integral. Now I'm going to divide by 2. So the integral of e to the x sine x dx is equal to 1/2 e to the x sine x minus e to the x cosine x. And I'm going to keep the c on the outside because a constant's still just a constant even if it's half of a constant. I know, what the heck was that? All right, so there you have it, guys. Anytime you get a trig and an exponential together, you're going to end up doing integration by parts twice and a little bit of algebra from back in the day, back when pogs were cool and all that other stuff. All right, have a great day. That's integration by parts. See you in the next video.